Okay, the last thing, it's embarrassing after over a semester, I finally told you what algebra was. Definition. Six- 16. Yeah. A and B are out. And remember, when we're talking about algebras in this course, in this universe, algebras mean over a ring, community ring of identity. Then an R algebra homomorphism is a ring homomorphism. Now remember, A and B are rings, but they're not necessarily commutative. So this is a ring homomorphism here, with a couple of caveats. B, the identity of A is the identity of B. And that's cool because I kind of assume that for all my ring homomorphisms anyway. And two, phi of RA is R phi of A. For all R and R, and S. So in other words, it is a ring homomorphism from the ring A to the ring B, but it also has the structure of an R module homomorphism, right? So it's a ring homomorphism, and it's also an R module homomorphism. Okay. So let's get to quotient structure. And the homomorphism. So the good thing about algebra again is you have these kind of recurring themes over and over again. And we're already almost all the way there when I talk about quotient structures and homomorphism theorems. And the reason is when I'm talking about modules, first and foremost, there are abelian groups. And we know all there is to know about quotients of abelian groups and the homomorphism theorems. And we're just going to add a little bit of spice to our meal by considering these R module homomorphisms. So let's get rolling with the following theorem. Let's let A and B, A, B, and C be modules. B and C in A. So A is an R module and B and C are submodules. One, the quotient group A mod B. So this is what I mean by we're halfway there. We know what this is. A is an abelian group, so any subgroup is normal. We know what this is. This is the cosets of A and of B and A is an R module. And of course, I've got to tell you how to scale multiple. Scale multiplication. R times A plus B is RA plus B for all A. So R as a scale multiplication. R times A plus B is RA plus B. This is a big thing in mathematics. If it ain't easy, don't do it, right? This is like the natural way to do it. And of course, RA is an element of A because A is an R module. In math, we call this D from A to A mod D given by IB of A. My input is A. Do what comes natural. Take it to the coset A plus B is an R module epimorphism. No surprise there. We already know that that's an epimorphism as a group homomorphism. So really all you need to do is check this homomorphism. And I wanted to say with kernel B, right, the kernel of that map is precisely the elements of B. Here's one of the homomorphism theorems. There exists an R module isomorphism. From B mod, the intersection of B and C is isomorphism, isomorphic to the module B plus C, which is the sum of these two modules. Everything in here is a little B plus B plus C. Modulo, it's submodule C. And for C is contained in B. And remember, by assumption, these are both contained in A. Then C mod, I'm sorry. Then B mod C is a submodule A mod C. And it's natural to ask what happens when you mod out. And that should be isomorphic to what? What do you think? Okay, so let's run through this briefly. We already know the quotient group is a vacuum Billy group. We've got that down. So all we really need is that the action is well defined. Right. So suppose so suppose you have two different representatives, X and Y, of the same coset. So is X minus Y is in B. All right. Therefore, R X minus Y, which is R X minus R Y, would be B. And so Rx plus B is equal to all y. And there you go. So my action is well defined. And of course, to show an R module, you need to show that this works well with, addition, right? You got distribution and so forth. But that follows from the fact that A is already an R module. So, for example, A1 plus B plus A2 plus B times R is R times A1 plus A2 plus B, which is R A1 plus A2 plus B, which is R A1 plus R A2 plus B, plus R A1 plus R A2, which is and the rest of them are just as tedious as that. A and B are R numbers. Okay. Number 2 is routine to check. And 3 and 4, I'm going to give this to right now, and I'll show you how there are consequences. But the next 2 are consequences of my favorite homomorphism, the first isomorphism theorem. So you can state the first isomorphism theorem a little bit more generally than this, if you like. But what we have here will be just fine. And then maybe we'll connect there. The others. Theorem 6.2. If F from A to B is an R modular homomorphism, then F induces an R module isomorphism F bar from R, from A mod kernel F onto the image of F. How many of you have seen the picture? You haven't really seen it, right? The way this works, sketch in. Let me know if you want to see more detail, but I mean, basically the way this works. Let's see, an input is so a typical element here. What's my output, I suppose? Right? If it ain't easy, don't do it, right? There's no widget to use. This is going to be in the image of F, so just plug that in. That better work. What's the burden of this proof? What's the thing that you have to show in the group theory? So well-defined is right. You need to show that this makes sense. If you have A prime plus kernel of F, you need to show that F of A and F of A prime. But since the difference is in the kernel, then that's exactly what you need. Right? Everybody satisfied with this? You want me to go further? So for example, the first isomorphism theorem is all over the place. And so we could look back to this one here. Isomorphism theorem. How do you suppose you could do this? You know, the thing that would really stink about showing these two things are isomorphic is the fact that they're, no matter how you try to cut this pie, these are both cosets, right? Which is obnoxious because it's got all that well-defined stuff. So if I were want to prove free, I would first define. I will let the first isomorphism theorem do that work for me. F from B to given by F of A is equal to what? What's easy? Don't do it. What's the easiest way to shove an element B into here? Take your little b plus 0. I emphasize that in C. All right. Now, the real question here, there's no question of well-defined, right? And it's pretty easy to verify that this is homomorphism because f of b1 plus b2 is b1 plus b2 and split the sum into 2. Everybody okay that this is an Armand homomorphism? For that? The only real difficult part of this is this onto? Right? But it kind of is. So I'm going to put that as a check. That's easy to verify. This is onto. Well, let B plus C plus C be B plus C mod C. Somebody give me a preview of that. B works, right? Because the difference of these two is known in C, right? The difference is B plus 0 and B plus C is known in C. So in this quotient structure, these two things are the same. So this maps onto. Everybody okay with that? And finally, what's the kernel of F? This is the set of B in B. What does it mean for this element to be the 0 element, B plus C mod C? If this is equivalent to the 0 element, what must be true of B? It must be in C. Therefore, the first isomorphism theorem gives that B mod the kernel of F is isomorphic to the image of F, or in our case, the kernel of F is exactly and the image of F is the whole thing. Everybody okay with that? Let me give you a corollary that's very important. I call this kind of the correspondence theorem. If R is a ring, B and A are R modules. Again, using our like ring, I think commutative, this could be a non-commutative ring, this I could call this left R modules. Then there's a one-to-one correspondence. Then there exists a one-to-one correspondence. Between submodules of A minus B and submodules of A and so it kind of works this way. With corresponding parts. Suppose you have some module X. It's a subset of A, but it contains B. X corresponds to, what do you think it corresponds to? What's submodule of A minus B? Well, how about X? There's an important way to think about this. This is kind of the easy part of the correspondence, if you will. The interesting thing to gather from this, in my opinion, is if I walk up to you on the street and give you a submodule of A mod B, then you can find a submodule of A with X, so that the one at random I gave you is X mod B, right? So any submodule of A mod B is in the form X mod B, where X is some module between A and B. This follows from 3 and 4 of previous the theorem before. So see if you can work through that. Okay. Any questions? Okay, so let me ask you all this. When you had, it depends on who teaches the algebra. When you had billion groups or groups, I don't know. Did you all, how extensively did you talk about the direct product and the direct sum? Well, so let's go. So let's, and this is actually important. Actually, I consider the direct sum being more important in some sense of the word. And you'll see why later, because it turns out that in a certain sense, the direct sum, even though the same kind of strength, because in a certain sense, it's smaller than the direct product, the direct sum is kind of the daddy mac of everything. So so uh, so yeah, a and an index set is a family of reviewing the groups. Then well, what is the direct product of this family of abelian groups? Well, it's a one called this a sequence because that index set might not Campbell. I'll use the word net to describe this because this might even be uncountable. But what this is, just think of this as a string, even an uncountable string, very large, where you have some ordering on it, and each AI in the ith coordinate, whatever that means, comes from that AI. Right? This is a direct product of a bunch of groups. Direct sum of AI is anybody know what this is? This is going to be very much like the direct product. Anybody know what the distinction is? Right. Yeah. The AIs are zero almost everywhere. And when I say almost everywhere, I mean an algebraicus almost everywhere, and not an analyst almost everywhere. This means all but finite and many infinite. So the direct sum, the restriction is this is a huge, potentially huge string of elements, but almost all of them are zero. Only finitely many are not zero. So whenever I say almost everywhere in reference to something, unless I tell you all otherwise, this means all but finitely many. This is a subgroup, of course, the direct product. Certainly, the direct sum is contained in there, and it's easy to check. It's a subgroup. What condition can I put on the index set where you have the same thing? Right, if the index set is finite, then there's no distinction, right? And that's why in elementary courses, I think a lot of times students get confused because they really don't understand the difference, because oftentimes they only deal with finite and many things, and in that case, there is no difference. So it probably doesn't take Gandalf to see where we're going here, because these are groups, right? And it's fairly easy to see that you can probably turn these into R modules if I just declare that these are R modules. And that's exactly what this will do. Theorem. Six, three, one. Yeah. I index set is a family of R modules. Then the direct and the product AI and direct sum AI are a direct product and direct sum of this family as abelian groups. as per my definition right here. Then one direct product that is an R module. With action given by R times AI what do? You just slide that R in. Just like that right in there, just like that. You do, I think, what you like to see the most natural thing to do. Two. Like sum. Product. Is or submarket. With comparative action. So now you just take the sub collection where almost all entries are zero. Notice that when you multiply R times this, again, you're going to have an output where almost all entries are zero. But, and in fact, categorically, you all are used to thinking of the direct product and the direct sum just as these objects, right? But actually, it's a little bit more. These are objects that are equipped with some special homomorphisms. And I'll tell you all about them. So the direct product standalone by itself is just this R module, but it's not really, more correctly, the direct product is that module equipped with these homomorphisms. For all K in the index set, the canonical projection I'm going to call positive from the direct product to AK given by how do you suppose this projection should work? Any ideas? There you go. It's AK. This is just a reader. That's what a projection does. It looks at this big string of things and it says, hey, I want the K coordinate. What is the K coordinate? AK. This is an R module. Homomorphism. And we're going to see that this family of homomorphisms makes the direct product a solution. It's universal. It makes it a solution to a universal mapping problem. We'll see that in a moment. D. For all K in the index set. So now I'm going to go for the direct sum. What do you suppose? Anybody want to guess what the map should be here? I mean, it's tempting to do the same one, but actually that's not the important one for the direct sum. The direct sum allows you to go backwards. For all K in lambda, the canonical injection, I owe to some K from AK into the direct sum. Given by, well, actually, I think the direct product one is easier to see what to do. Actually, what do we do here? How do we go from the single element of AK and build some natural element inside the equation? Yes.
Everything else is zero.
Okay, good, good, good. So I'm going to call this sequence XI with XI equal to AK times K and 0 else. So in other words, what you do is you sort of make the analog of this here. That is, you put AK where the K core is supposed to be, fill anything else else. And this is an R module. I want you to notice something here. It's a recurring theme that will come up later. The direct product, you have the canonical homomorphism projections. They go from the big direct product out into the components. And these are all R module epimorphisms. For the direct sum, it's the other way. You go from the components into the direct sum, and now it's R module monomorphisms. So how many of you all saw this or know of this from just from abelian groups or groups? Joe. Okay, well, let's see what we have to do. See what details we have to fill in. How many of you are convinced that this thing is indeed an R module with this action? So everybody good with this? And how about this? This is an R submodule with this action. Everybody cool with this? Okay. Let's check this out. Let's look at C here. Let's let pi k go from, let's look at the index step. Pi k goes from direct product AI object. Let's quickly check if this is an R module homomorphism. Okay, well, notice I can write this. It's A plus A prime. Agreed. And just by definition, this is AK plus AK prime, or A prime K, yes, which is equal to pi K AI, or pi K AM. Okay, so I'll verify that this is an ability group. Right? What about our module? Well, if you look at type A of R. Let me see, to apply my rule here, I guess I need to slide that inside. Okay. And this is RAK, which is R, times 5K. And I hope it's fairly clear what this is on to. Because notice, if AK is in AK, then uh, it's such that pi k of xi. So it's on to. Right, and of course, I picked this sort of at random, but I could pick any crazy element. All you need is the element to have AK and K coordinate. Are you okay? Check number D, but the proof of this is along these lines, and that's difficult. Okay, any questions? Andy? All right, so. I'm gonna put down the next theorem. Actually, the next two theorems. And I'll come back to the proof of, I guess, the first one. I'll let you prove the second. But I'm gonna show you kind of the cool thing about direct products, direct sums, and universal products. Okay, so theorem 632. But R be a ring, AI a family of R modules. AI minus an index set, a family side of easier family of R modules. And C an R module. And these things, PI. A family. R module. Okay, so that's my setup. I have a ring. These are R modules. And C is an R module, and these PIs are all R module homomorphisms. from C into AI. Now, the first time I ever saw this theorem, it bothered me a little bit because I was like, how do you know they're homomorphisms from C to AI? Somebody, please lay my initial naive worries to rest. There should always be homomorphisms from C to AI. Why? If nothing else, some of them might be the zero homomorphism, right? So it's not like there's a great deal leaning on this. You can, if I walk up to you on the street and give you a family of R modules in C, for sure, I could do this just by letting all these be the zero homomorphism. But then, maybe there's ones that are more exotic. Then there's a unique R module homomorphism. There is this unique R module homomorphism. Apple theme from the direct product of AI from C into direct product. Such that B is equal to BI for all I and I think that's the direct product of AI is uniquely determined by this update. Let me draw, I like to draw this diagram to sort of illustrate this point. What we have here is C, the AI, this guy. Actually, let me and here you have the direct product of AI. Now, what we have here, we have the projection map here. It was pi k, right? And here, C. So there's a unique homomorphism that goes from C to the direct product, such as this diagram commutes. That is, if you start with a C and you go here, here, it's the same thing that you got from your family of homomorphisms. And this is the solution to the problem. The problem is it's a unique solution. Any module that behaves this way, equipped with these functions here, is isomorphic to the direct product. That's what we mean by a unique solution to this mapping problem. The direct sum, I want you to take a look at this, and we'll talk more about this later, is the dual. Same setup. But now we have a family of R module homomorphisms. R module B and family of homomorphisms PI from AI into D. So now instead of going from C into the components, we're going from the components in D. Then there exists a unique harmonic homomorphism. Capital psi from the direct sum of AI D, such that we have the diagram commuting, that is E over K is equal to EK, roll K, and the index set. And again, the direct sum is uniquely determined by this property. So the diagram here, notice and now we have these inclusions. And now what happens is we have a map instead of into the direct product from the direct sum. Notice how these are called dual space or mirror images. Direct sum is a solution to this problem, direct product is a solution. We will delve more into this mystery next time. Any questions? All right, I'll see you folks on Wednesday.